Hello everyone, I'm William Fawcett, and today I'll be talking about some recent supersymmetry searches from Atlas. I'll be covering 3 searches today, each of which targets a different challenging scenario. The first is the 4-lepton search, which targets the electroweak production of supersymmetry. The second is the disappearing track search, which targets ultra-compressed models. And the last is a brand new search for long-lived stop particles. In the SUSY group, we typically search for the production of a pair of supersymmetric particles. Almost nothing is known about these particles. They could have almost any mass and could decay to a variety of both SUSY and standard model particles. This gives rise to a rich and complex decay structure, which has certainly kept us busy over the years. But this also means there's plenty of places left for us to look. Generally, we split our efforts into looking for either specific production mechanisms, as I've shown here, or specific final state signatures. One thing we do know about the particles is their hypothetical production cross-sections, which are shown in this plot. I've drawn a line across the plot here, which corresponds to where we would expect about 10 events from the full run-2 dataset collected by Atlas. You can see that we're pushing multiple TeV for the gluinos, the stops, and the squawks, just over a TeV for the electroweakinos, but crucially, less than a TeV for the leptons. There's a lot of motivation for SUSY, which I won't go into here, but the updated G-2 result gives us a nice reminder. Here I show SUSY models of lots of different kinds simulated by Atlas for the run-1 PMSSM scan. Each bin of this 2D plot contains many viable SUSY models. The axes here are the modified G-2 predicted by SUSY and the mass of the SMU1 in those SUSY models. We stopped simulating models that were beyond the 3 sigma of the previous experimental limit, which is shown by the dashed line here. The new limit is even further away from the standard model, and had we not stopped simulating, we would have found viable models in this region here as well. The new G-2 result, if confirmed, would help us hone in on the kinds of SUSY models to look for, notably those with sub-TeV SMU1s. Okay, so onto the searches. The first search that I want to cover is what we call the 4-lepton search. Here's a display of one of the events that went into one of the signal regions with 2 electrons and 4 mu1s. This search targets 2 classes of models. The first class is an R-parity conserving model, such as the example shown here. In this example, we start with the production of Higgs-xenos, which are highly theoretically motivated due to their role in naturalness, but difficult to find as the charged and neutral Higgs-xenos states are very compressed. This search gets around this problem by considering a GGM scenario, which introduces the ultralight gravitino, which the Higgs-xeno can decay into via a Z or a Higgs boson. We choose events with at least 4 electrons or muons, which are in pairs consistent with a Z boson. We veto B-jets to remove the Higgs to BB component, to which this analysis is not sensitive, in order to reduce backgrounds. There's no requirement on the number of tau leptons, and the signal regions are split into 2, depending on an AT miss requirement. A second class of models chosen to search for by this analysis are R-parity violating models. R-parity is normally needed to prevent SUSY from allowing rapid proton decay, but this can be avoided if a certain number of these RPV lamp decouplings are turned on. Here we target the BINO. However, the pure BINO production cross-section at the LHC is very small. And so to get around this problem, we consider other production processes, such as Wiener production, lepton production, and gluino production. In the case, the BINO decays via an RPV coupling to 2 leptons and a neutrino. There's many RPV couplings that could have been turned on, but this analysis focuses on the 2 scenarios listed here, where the leptons can be either electrons or muons, or they can be taus and either electrons or muons. The signal regions are split depending on the lepton requirements shown on the right here, with different combinations of light leptons and taus. The main backgrounds to this analysis are split into 2 groups. The so-called reducible backgrounds, which is mainly ZZ and TTZ, which are estimated with Monte Carlo and normalized in control regions, and the so-called irreducible backgrounds, which arise from W or Z plus jet processes, or TT bar, where one of the jets fakes 1 or more leptons. This background is estimated with the fake factor method, which is a loose to tight method, where the probability of a loose fake lepton making it into a tight signal region is estimated in data. The ZZ and TTZ backgrounds dominate the light lepton regions, and the fake backgrounds dominate the region with taus. You can see an example of some of the control regions here, and you see a nice agreement between the data and the background prediction. Here's the results. As you can see, there's no significant excesses. In particular, previous iterations of this analysis had an excess with the partial data set. These regions have been re-implemented with the full data set, and sadly, there was no increase in the deviation. One thing I really like about this analysis is that we included a general 5 lepton signal region. This isn't motivated by any particular BSM physics models, but could have sensitivity to something we haven't thought of. And for a full definition of the signal regions, see the backup. Here's some examples of interpretations of the SUSY models that this search was optimized for. On the left is the RPC model that I mentioned first, and you can see that we vary the Higgsino mass and branching ratio of the decay to the gravity known as Z. As the branching ratio increases from 30 to 100%, the limit of the Higgsino mass increases from around 100 to 600 GeV. On the right is one example of the RPV model, in this case starting with slepton production. Here the limit on the slepton mass depends on the decay mode, with limits just over a TeV in the case of decays to electrons and muons, and around 800 to 900 GeV in the case with decays to taus as well. The next search I'd like to talk about is the disappearing track search. Here's an example of an event that made it into one of the signal regions. As you can see, it doesn't look like there's much going on here, but that's precisely the point of this analysis. This search targets the ultra-compressed Wino or Higgsino, either through direct electroweak production, as shown here, or via strong production, as shown here. The key thing with the Wino or the Higgsino is that they have a small mass splitting between the chargino and the neutralino. And this can lead to a long-lived chargino. Typically with lifetimes around 0.02 nanoseconds for the Higgsino and 0.2 nanoseconds for the Wino. This can lead to the case where the chargino is stable enough to transverse through a few layers of the Atlas inner detector before decaying into a soft pion and a neutralino. The soft pion has too little momentum to be reconstructed by Atlas, and so this gives the signature of a track that just disappears. We select the events by triggering on missing transverse energy, and we have 2 streams to the analysis where we target the different production mechanisms with differing MET and jet requirements as shown here. No excess was seen over the background predictions for this analysis, and so limits can be set on the Wino and the Higgsino. These two plots show quite interesting limits. As you can see, overlaid is this gray dashed line, which corresponds to the lifetime of a pure WeKnow or Higgsino for the left and right plots, respectively. Where this line crosses the limit of our sensitivity gives a limit to the pure WeKnow and pure Higgsino with limits of about 660 GeV and 210 GeV, respectively. The last search I want to talk about is a search for long-lived stopped particles, which is a very new search which was just published in April. This is a really unique search that looks for BSM long-lived particles that carry a standard model charge. For example, a long-lived particle could be produced in proton-proton collisions at the LHC. This particle could bond with standard model quarks to form an R-hadron, for example, which loses momentum as it traverses through the Atlas detector material. If the particle is long-lived enough, some of these will stop inside the detector before decaying. In this search, we're looking for the late decays of these particles to hadronic jets, and we can target lifetimes from microseconds to years. One really innovative thing about this search is that a completely new dataset had to be constructed just for it. Here we trigger on empty bunch crossings in between physics fills of the LHC. The signal region requirements are requiring a jet PT greater than 150 GeV, a primary vertex veto, a muon veto, and then there's two signal regions split by the requirement on jet eta, less than 0.8 for SRC and less than 2.4 for an inclusive signal region. Another challenging aspect of this analysis was the background estimation. One of the main backgrounds comes from cosmic muons, which can introduce an energetic jet. This occurs when a cosmic muon undergoes Bremsstrahlung and releases high energy photon, which can be reconstructed as a jet. This background is removed with impact parameter style geometric requirements between the jet and the muon spectrometer segments. The plot on the right here illustrates this requirement and the definition of this alpha variable that they cut on. The curved line in this eta phi space corresponds to the straight line on the plots on the left. And this alpha is the impact parameter style distance from that line and the jet. And as you can see in the plot on the bottom left, they are able to remove most of the cosmic muon background with this requirement on alpha less than 0.2. Another major background is beam-induced backgrounds. This is caused by stray protons interacting with residual beam gas or with the LHC instrumentation, for example. And other backgrounds include calorimeter noise and Kaplan background. Here's some results from this search. On the left, you can see a plot of the 28 data and includes their background estimate, which you can see is dominated mostly by the cosmic muons and the beam-induced backgrounds. Sadly, there's no significant excesses, and so limits on the gluino mass could be placed, and you can see that on the right-hand side. This analysis is sensitive to gluino masses up to 1.4 TeV in the lifetime plateau, which is from around 10 to the minus 5 to 10 to the 3 seconds, and up to about a TeV for lifetimes of around 100 nanoseconds, and then also up to 10 to the 7 seconds. And if you're interested in this search, see this wonderful CERN physics briefing for some more info. Before I conclude, I just want to point out a few very other recent Atlas searches that have been published in the last few months. So do check out these as well. To summarize, we haven't seen any hints of SUSY at the LHC so far, but there's still a myriad of places to look. And we've seen some really inventive ways to search for SUSY. We're covering the full spectrum of production mechanisms, We've taken on the challenging Higgsino with the GGM scenario. The disappearing track analysis takes on the ultra compressed Wiener Higgsino directly. And we've seen this really innovative search for stop particles with a custom data set that's been able to rule out a large number of BSM theories. So stay tuned for more SUSY searches to come, and thank you for listening.